Hi guys, good morning. Is everyone ready? Shall we start?
Yes, sir.
Only three of you are there. We'll wait for, I think, 2 more minutes. Let everybody join. Okay, it's 7:05. I think we'll start, right? Okay, so if you can remember what we saw last class, like we saw Boyle's law, right? So it's just a mathematical equation. Like it's a statement saying that pressure and volume are inversely related, right? When you have constant temperature and pressure, right? Okay, so we saw the mathematical forms of that. We saw different equations of that, and I taught you certain things about logarithms, right? So that's what we saw last class. Okay, and I just wanted to start with one point, right? Saying that the graph which we saw, right? So I have PV, I mean P versus V graph, right? And I saw that the graph is going to something look like this, right? Because the pressure and volume are inversely related. What is the name? What is the shape of the graph called as? What is the shape of the graph called as? Guys, I told you you don't have to remember that, but still, do you remember what is the shape of this curve? Hello. So I assume that you don't remember.
Rectangular hyperbola.
Ah, correct. Right. So the shape of this curve is what is called as rectangular hyperbola. Right. Okay. Now this particular curve which I got here, these graphs, right? So whenever you do something, right? Whenever you plot a graph, when you have constant temperature, right? So those kind of graphs are what are called as isotherms, right? So what do you mean by isotherms? Isotherms are graphs, right? Graphs at constant temperature, right? So this whatever we do here, like with P versus V graph, right? We the in the statement itself we told that it is going to have constant temperature, right? So obviously this particular graph here is going to be called an isotherm, right? Iso same, term means temperature, same temperature, right? Okay, right. So the now question is, if I plot, this is for say temperature T1, right? This particular graph was plotted for temperature T1, right? All the points, the temperature is same T1, right? Say now I have one more this thing graph, say 2 more graphs, all these are plotted at different temperatures, T2, T3, right? Fine. So from the graph, right, if I ask you, can you predict what will be the order of magnitude of T1, T2, T3? Will you be able to predict what is the order of magnitude, that is, which is greater, whether T1 is greater, whether T2 is greater, or T3 is greater, right? So will you be able to tell that from the graph?
No.
You will not be able to tell it from the graph. Okay, you will be able to tell it from the graph. Very simple, right? But obviously, for you to answer this, you need, I told you, there are three other laws. Along with Boyle's law, there are 4 laws, right? So maybe you require some other laws, right? But still, if you're logically sound enough, right, you will be able to answer this question, right? Okay, now how are we going to go about it, right? Okay, so for this purpose, like for finding out what will be the value of T1, T2, T3, right? Let me make, say, volume constant, right? Let me make volume constant. Even you can do pressure constant, doesn't matter, right? Say if I take one particular volume, say I will take this particular volume for all the isotherms, like 3 different graphs. For all the isotherms, I take one common point, volume, one common volume. Okay, right? And I see what is the pressures, right? Say for T3, the pressure is P3, and for T2, the pressure is say P2, and for T1, say the pressure is P1. Yes, no problem. Okay, right. So from this, we will not be able to tell exactly temperature, but from the y-axis points, that is P3, P2, and T1, which is greatest?
P3.
P3, obviously, we plot along the y-axis, obviously P3 is the greatest value. So definitely I can say that P3 is greater than P2, greater than P1. Okay. Now, logically think and tell me, how do you think pressure and temperature are related when you keep volume constant? Think of a real life situation. Are they directly related or are they inversely related? Go for a practical situation. Assume that where somewhere volume is constant and you're heating something, and if there is a gas inside the vessel, what will happen to the pressure of the gas?
It increases.
Definitely, right? So that eventually we'll be calling it as Gay-Lussac's law, that is pressure and temperature are directly related, right? So obviously you can understand, right? Say I have a vessel, right? In that I already have a gas, right? Say it has some pressure of P1, right? Now if I start heating it, now what will happen? When I start heating it, now I already know that the pressure here which is coming is because of the kinetic energy of the gases. Because of the kinetic energy, gas molecules will be moving, they'll be undergoing collision of the walls of the container, and that is why I have this pressure, right? Now if I increase the temperature, if I give some energy to the molecules, they will move faster, right? They will move faster, they will go hit with a greater force through the walls of the container, and obviously the pressure increases. Obviously volume is constant. You can see that the volume cannot change. It's a closed container, right? The volume cannot change, so meaning that definitely if temperature increases, the pressure of the gas also increases, right? So if this is the order, P3, P2, P1 is the order, what will be the order of temperature then?
T3, T2, T1.
Yes, exactly. So if P3 is the greatest, definitely T3 is the greatest because P and T are directly related, right? So T3, T2, T1 will be the order. Okay, so this question can also come in your exams. They will give 3 different isotherms, right? Ask you to find the temperature order, which is greater, which is lesser. All these things can be asked. Okay, fine. So that is about Boyle's law, right? Okay, we'll move on. We'll move on to the next. So next law after Boyle's law is my Charles law. Okay, take the statement, write it down. At constant pressure and number of moles, at constant pressure and number of moles, the volume of the gas at constant pressure and number of moles, the volume of the gas is directly proportional to the temperature of the gas. Right? Volume of the gas is proportional to the temperature of the gas. Okay, right. So looking at this statement, can you give me one real life example where this happens? Volume. So look at the statement. They say that at constant pressure, the volume and temperature are directly proportional. Can you think of any real life situation? That means if volume increases, if temperature increases, volume also increases. That's what you need to know. Any real life situation can you think of? Anything, right? So we know that if something is heated, definitely they will expand. Things on heating will expand, isn't it? So what do you mean by expansion? Definitely I'm going to have increase in volume. Okay, so let me do it in the form of an experiment. Let me put in some real life cases and we'll see whether this is true or not. Okay, fine. So assume that I again have my piston arrangement. Okay, right, I have a piston arrangement and I have a gas inside. Okay, right. Say initially, say I'll call the pressure as, pressure is P1, pressure is P, I'll call it, right? Pressure is P and the volume is V1. Okay, now it's an equilibrium. I'm not doing anything, right? Okay, again, I told you that this piston can move up and down, right? So if you can remember last time what we did, we placed a we placed a 5 kg mass and we said that obviously that the piston will go down, reducing the volume, pressure increases, volume decreases, all those we saw. But this time what I'm going to do is that I am going to heat this piston. I'm going to heat this arrangement. Okay, I'm increasing the temperature basically, right? Okay, so initially say the temperature was also T1. Now when I'm heating, say assume that the temperature went to T2, increased. Obviously T2 is greater than T1. That is there, right? Now, if like as you please understand this, if this was hinged, what do you mean by hinged? Like the piston cannot move up or down, it's closed, right? That means the piston cannot move up or down, it's hinged, right? If that is the case here, if that is the case, what is constant? You tell me.
Volume.
Exactly, right? If I'm making sure that this is not going to move up or down, definitely it's a closed system, volume is not going to change. But here that is not we are interested in, like it's not going to be hinged. Okay, so now I'm heating the vessel, now I'm heating the arrangement, right? So what will happen now? You tell me.
The piston will move up.
Exactly, right? So because now the piston is here, now after say if I bring it to T2, this thing would have been here. The piston would have been here, right? Because again the same reasons, right? So obviously the gas molecules will try to hit the walls of the container with greater force right? With greater force. So if this was not moving up, the pressure would have changed. Is it not? Because the volume is constant, volume cannot change. So in order to, like, say, accommodate all these things, like, the pressure would have gotten increased because it is going and hitting the walls of the container with greater force. But in this case, what you're seeing is the volume is increasing, the pressure, the piston is moving up, making sure that the pressure is still the initial pressure, that is my P value. Okay, here also in this condition also the pressure is P. The initial condition also pressure is P. The only two things which have changed is volume and temperature. And both things, you have increased the temperature and you can see the volume also got increased to V2, where V2 is greater than V1. Yes, right? Everybody understood the scenario here? What happened? Any questions here? Guys?
No, sir.
Okay, so everybody understood, right? When I increase the temperature, making sure the pressure is constant, the volume increases, right? So I can put it in the mathematical form. T is directly proportional to V. This is the mathematical form of Charles' law, right? And if I put a constant, P is equal to K into V, right? Or I can say that the division of T and V is always a constant, or how I wrote in the previous case, I can write like T1 by V1 equal to T2 by V2, so on and so forth, is some constant, right? T1 by V1 equal to T2 by V2 is equal to T3 by V3, so on and so forth. Oops. Okay, so yeah, will be constant, right? Okay, this is my, what is that? Charles law. Okay, now let me go to the graphs, right? Or how the graph looks for Charles law. We'll see that. And in your statement, if you miss what is constant in your exams, if they ask you, for example, Charles law, and you just say that temperature and volume are directly related, they'll not even give you half marks. You should mention that the pressure is constant, the number of moles is constant, right? Only then the statement is valid. Okay, so anyways, so now we are going to plot a graph between temperature and volume. Okay, right, so please understand that the temperature is in Kelvin. Temperature is in Kelvin. Volume doesn't matter, right? Okay, how do you think the graph is going to be, people? How do you think the graph will be? T versus V graph. How do you think the graph will be?
So will it be the same as that PV graph? Will it
In
be the
PV
same?
graph, pressure and volume are inversely related. So that's why I got a rectangular hyperbola, right? Now here, T and V are directly related. And you can see, you should not be predicting it from whether it is directly related, or, like, you can predict it, but the easier way to go about is by using this equation. T is equal to K into V. So this is of the form of what?
Y equal to
Y
mx.
equal to mx plus.
Exactly, right? So this is of the form of Y is equal to mx, right? Where Y is my T, right? V is my x, and obviously some constant would have been the slope, m, right? So we can say that this is the Y is equal to mx plus c. So is it going to go from the origin?
Yes, sir. It will be a straight
Okay,
line.
right. Okay, it will be a straight line going through the origin. That's what we think. It is going to be a straight line, no doubt about it. But there is one thing which you need to know, right? The thing which you need to know is, when I have zero volume, like, say, when I have zero volume and there is no volume, okay, and what you see here is the temperature is in Kelvin, Okay. Now, if you want to reach 0 Kelvin, okay, if you want to reach 0 Kelvin is how many degrees Celsius? You understand my question? I have 0 Kelvin. What is the value of 0 Kelvin in degrees Celsius?
Minus.
Correct. Minus? Minus?
Minus 273 degrees.
Yes. It's going to be minus 0 Kelvin is minus 273 degrees Celsius. Okay. Right. Fine. Now there is a problem with this temperature. There is a problem with this temperature. And what is the problem? Is 0 Kelvin. This is what is called as absolute zero of the temperature. Right? The 0 Kelvin. We'll speak about it more in thermodynamics, but still, I'm just giving you the introduction. So this 0 Kelvin, right? The 0 Kelvin is what is called as your absolute zero of the temperature, right? You will be studying certain laws in thermodynamics also. Say first law, 0th law of thermodynamics, first law of thermodynamics. Sir, I'm having a network problem. I'll be yeah, sure. Take your time, right? So what I was telling, yeah. So you'll be studying 0th law of thermodynamics, first law of thermodynamics, second law, third law. All these things you'll be studying. Okay. So in that second law of thermodynamics, right? Second law of thermodynamics says that 0 Kelvin cannot be reached. 0 Kelvin cannot be reached. Until now, we have so much advanced science research, all these things, technologies coming up, but still we have not reached 0 Kelvin. We have reached almost 0 Kelvin, but nature does not allow you to reach 0 Kelvin. Okay. So if this is true, if T is directly proportional to V is true, right? So when I have 0 Kelvin, I should have 0 volume. Is it not? Right? When I have 0 Kelvin, right, I should have 0 volume. Right? But again, we know that 0 Kelvin cannot be reached. Right? We know that 0 Kelvin cannot be reached. So the graph, where will it start? Right? Where will it start is not from the origin. Right? It is not going to start from the origin. It is actually going to start from somewhere here, below the graph, right? From some negative temperature, right? From some negative temperature. Actually, I would say that in 0 Kelvin, the actual graph, I can say it's not going to start from here. The actual graph will be like this. The actual graph would be something like this. So now, what do you understand from this graph? Right. So obviously at this point, volume is 0. Is temperature 0? Tell me. Oh wait, volume is not 0, right?
Volume can't be 0, no, sir.
Yeah, volume is not 0. Correct. So volume, there is some volume.
Temperature 0.
But
If it intercepts x-axis.
I think I'm drawing the graph wrong. 1 second.
It pass through y-axis only, no, sir.
Oh yeah, it should be here. Correct. Right, so it's not going to start from here. It's going to start from here. Yeah, this is going to be the graph. Okay, so now what you see here is if I take this point, right, I have volume is 0, right, and temperature, obviously I have some value. Okay, so why all this drama is because you can see that 0 Kelvin cannot be reached, right? 0 Kelvin cannot be reached, and that's why we don't start from a point where temperature is 0 Kelvin. We should not start it from that point. Okay, so we should start from this point only where temperature is not 0, even though volume, ideally speaking, cannot be 0, but still compared to temperature, volume is okay, manageable. Okay, because there is no law as such in chemistry saying that volume cannot be 0. But there is a law in chemistry saying that temperature cannot be 0 Kelvin. Okay, right? So the graph will eventually be looking like this. Understood? And if you want to, if you extrapolate this graph, this tell me it is 0 Kelvin, obviously. And at 0 Kelvin, I know what is the temperature, minus 273 degrees Celsius. So this is how you should, if you should go, what is it? Plot the graph. You can ask me, sir, at this point, I have negative volume. Let it be. But anyways, we are not going to worry about those situations because that cannot be reached. Do you understand what I'm telling?
So we look only to the first quadrant now, sir.
Sorry.
So we see only the first quadrant values.
Exactly. We are concentrating only on the graph. Before this, actually, this point itself cannot be reached. That's the truth. 0 volume, like it doesn't sound good, right? So starting from this point itself is a question mark. So beyond this, no, we are not actually going to care about it.
Yes,
Okay.
sir, understood.
Right? So yeah, this would have been the graph. It's a straight line. It is directly proportional. But since I'm doing temperature in terms of Kelvin, it cannot start with 0 Kelvin. That's what I'm saying. Okay, right? Cool. So that is what is my what is that? Temperature versus volume graph. Okay. Now again, I can make this question a little tough by asking. This is at pressure P1, pressure P2, pressure P3. Now we know that your pressures are constant, right? For all these curves, there is one pressure, some pressure, P1, P2, P3, right? So now again, can you look at the graph and tell me what will be the orders of P1, P2, P3? So these kind of graphs are what are called as isobars. What do you mean by isobars? Isotherms are graphs at constant temperature. Isobars are graphs at constant pressure. Bar, we know, is a unit of pressure, right? Iso, same pressure. Okay, so anyways, tell me, what will be the order of P1, P2, P3?
So if we
Same thing,
substitute in the equation, temperature will be inversely proportional to pressure, sir.
Don't do all that. I told you how to do it. Fix one thing, say fix volume and see how temperature is changing. And obviously you will be able to get the relationship. I told you, we just exactly did the same thing in PV graph. Just before this we did. Do the exact same way.
I mean, P1 is greatest, P2 is second, P3 is third.
Okay, yeah, correct. Right, so we can do that. Say in this case, let me do it the opposite way around. I'm not gonna make a volume constant. Let me make temperature constant. Okay, I will take one single temperature. Okay, so now this would have been my V1, this would have been my V2, and this would have been my V3. No problem. Okay, fine. So from this, I can obviously say that V3 is the greatest, right? V3 is the greatest, then V2, then V1. That's the volume order, right? And I know if I have constant temperature, volume and pressures are
Inversely related.
Inversely related. Why is it that nobody's answering? Yesterday was good. Is just because you just woke up now? You're feeling so sleepy, people. Concept, like everybody has to involve. Doesn't matter whether you give me a correct answer or not, but you must involve. Okay. So anyways, so we see that V3 is the greatest, V2 is less, and then the least is V1. And I know volume and pressure are inversely related. So if V3 is the greatest, P3 is the least. If V1 is the least, P1 is the greatest, because volume and pressures are inversely related. So if this is the case, P1 will be greater than P2, will be greater than P3. Okay, now even if you would have made volume constant and checked, the same I would have got. P1 greater than P2 greater than P3, the same thing I would have got. Because I know pressure and temperature are directly proportional. That is the next law basically that we'll see. Okay, right? So that's about Charles' law. Okay, right? So now we'll move on. Right. So hope I can solve this. Right, so next one, third law, is what is called as my Gay-Lussac's law. Okay, G-A-Y, Gay-Lussac's law. Okay, take the statement. At constant volume and number of moles, at constant volume and number of moles, the pressure of the gas is directly proportional to the pressure of the gas is directly proportional to the temperature of the gas. The pressure of the gas is directly proportional to the temperature of the gas. Simple, right? So now I have two variables constant, that is my volume and number of moles, and the other two are varying, that is my pressure and temperature. And we already saw, we saw practical examples when I have a closed container and I start heating the vessel, obviously the molecules will move faster, thereby hitting the walls of the container with greater force, thereby exerting more pressure. We already saw the explanation for this, right? Okay, so we'll just go for directly the mathematical equation for this. So they say that pressure is directly proportional to temperature, right? So I can write, or let me write it like this: T is directly proportional to P, and T is equal to K into P, some proportionality constant, right? Or I can write it as T1 by T1 equal to T2 by T2, so on and so forth. Tn by Pn is always a constant. Okay, right. So now if I plot the graph, again T versus P, what do you expect? What do you expect from the graph? How do you expect it to be? Look.
It'll again be a straight line, sir.
Okay. It is going to be a straight line. Anything else?
It won't start from origin.
Correct. Right? Exactly what we did in the last case, saying that we cannot reach 0 Kelvin. Right? The 0 Kelvin cannot be reached. Right? So definitely we are not going to start from origin. Right? So we are going to start at some point where temperature is not 0. Pressure can be 0. No problem. Right? So we will put a graph like this. Yes? Okay. Right? So again, you can have, if you go extrapolate this, I will have a negative pressure, but again, we are not going to worry about it. Please don't worry about it. Okay, fine. So this is how the graph looks. Again, I can have this itself, V1, V2, and V3. Right? So now you do it and tell me what is the order of volumes, V1, V2, V3. Now you can make anything constant, either T constant or P constant, and you can see how is it varying. Accordingly, you will be able to tell what is the order of volume.
So V1 greater than V2 greater than V3.
Okay, correct. Right. So let me make pressure constant this time. Okay, let me take one pressure, right? And I'll see how the temperature is varying. This is T1, This is T2, and okay, bear with it. This is T3. Okay, right? Fine. So obviously, I see that temperature T1 is the greatest in the y-axis, and I know temperature and volume are directly proportional. Just now we saw Charles' law, right? Temperature and volume are directly related. So if T1 is greater than T2 greater than T3, definitely V1 is greater than V2 greater than V3. That would have been the answer, right? Okay, that's the third law. Okay, now the last law is fourth one. Avogadro's law. Okay, take down the statement. Right. So it says at constant pressure and temperature. At constant pressure and temperature. Same volumes of different gases at same pressure and temperature, same volumes of different gases, same volume of different gases will have same number of particles. You can even say same will have same number of particles. In the bracket you write number of moles. Right, so repeat the statement. At constant pressure and temperature, same volume of different gases, right? Same volume of different gases will have same number of molecules, same number of molecules, and in the bracket you write number of moles. Okay, right? So, fine. I think you would have done writing the statement. Now, if you analyze the statement, this statement we already saw in your first chapter, is it not? How? This statement we already saw in first chapter. Can you tell me how? First chapter being some basic concept of chemistry. Let me see. I'll give you one.
Like how means?
How means we already proved this statement in the first chapter. Think. What are the three definitions of moles? And the clue is one of them talks about volume. If you can bring that statement here, it's proved. We know there is a definition, right? For number of moles, there are three definitions. One in terms of mass, one in terms of number of particles, and one in terms of volume. So just recollect what and all were the statements, and especially if you can recollect what is the statement regarding volume, this is sorted. This particular law is sorted. We'll go one by one, right? Fine. I think I have to pick one guy or pick one girl and ask, Divya, are you there, Kana? Divya? Okay, I think there's a problem. Okay, Venisha, are you there? Venisha? Okay, fine. Shruti?
Yes, sir.
Kana, can you tell me what is the definition of moles in terms of mass, in terms of weight?
Volumes are like 1 mole of any gas at STP will like that
Hmm.
will occupy.
Anything. If you want to tell, if you want to tell in terms of volume, well and good. Tell me what is it in terms of volume? 1 mole of any gas.
Gas at STP will occupy a volume of 22.4 liters.
Wonderful, right? That's the statement. 1 mole of any gas. No, it doesn't matter what gas it is, right? 1 mole of any gas at STP. What is STP? Standard temperature and pressure. It should be that pressure and that temperature. At that pressure, any gas will occupy a volume of 22.4 liters, right? So then we got a equation for number of moles with respect to volume, right? Given volume divided by 22.4 liters, right? Okay, and then this is one of the statements. Now let me connect, or I want you to connect the statements for, the definition for moles with respect to number of particles. You tell me. Moles and number of particles, how are they connected? Okay, I think I will call someone. Okay, Abhishek.
Yes, sir.
Kana,
Sure.
can you tell me what is the definition of moles with respect to number of particles? Yes.
Sorry, sir. I don't know, sir.
Okay, no problem. Right. Fine, I'll ask someone else. Mithun, are you there? Oh, Mithun, I think will not be able to speak, right? Mithun, can you text? Mithun? Okay, I think again there's a problem. What is happening? Like, why is it that Divya, Venisha, Mithun, all these people are not able to answer? Okay, fine. There is Nagaraj. Who's Nagaraj?
I think that's Bhavadayani, sir.
Oh, that's Bhavadarini.
I think
Yes,
so,
sir.
Okay. 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 So Bhavadarini, are you there?
Yes, sir. Can you repeat the question, because I just left because I had poor connection, sir. I rejoined
No
just
problem.
now.
No problem. So what I asked is, I have definition of moles with respect to number of particles. We have studied this in first chapter. I want you to tell the definition.
1 second, sir.
Yeah.
Sir, 6.022 into 10 to the power 3 hour. 1 second, sir. I'll
You're correct. Tell it.
1 mole is equal to the Avogadro number of particles, sir.
Okay, correct. Right. So what you said, I understand. So how you have to properly put it is 1 mole of any substance, right? 1 mole of any substance, again at STP, right, will have Avogadro number of particles, right? And Avogadro number value is 6.023 into 10 to the power 23.
10 to the power 23.
Yes, good, Bhavadharani. Okay, so yes, that was the statement. So I have one more, in terms of number of moles, which says that it's given number of particles divided by the Avogadro number. Na represents Avogadro number, right? So what this statement says, if you look at Avogadro's law, what it says is that at constant pressure and temperature, same volume, that is, say I have, what I'm saying is, okay, let me draw a new diagram, wait. Right, so I have, say, assume that I have H2 gas, O2 gas, and say N2 gas. Different gases. For all of them, I have pressure, volume, and temperature to be same. I told you, at constant pressure and temperature, same volume of different gases, same volume will have same number of particles. Okay, now how will I prove it to you? Say, assume that assume that the volume is 22.4 liters itself. In all the cases, right? In all the cases, the volume was 22.4 liters. Okay, fine. So now, if that's the case, can you tell me how many number of moles of each of these are there? Looking at these two statements, like forget about the number of particles. I'm asking about number of moles. Looking at this, if I say that 22.4 liter of all these are there, what is the individual volumes of all these? Sorry. What is the individual number of moles of all these? What happened? I'm saying that at some pressure, okay, assume that the pressure and temperature are standard pressure and temperatures, 0 degrees Celsius and 1 atmospheric pressure. Okay, now tell me. Just now we saw, right? All of the gases, all of them are at STP, right? And all of them are having same volume, that is 22.4 liters. So what should be the number of moles of all these gases?
Will be same, sir.
It will be same. What is the value? One mole, right? 1 mole of any gas at STP will occupy a volume of 22.4 liters. Now I'm just telling you the opposite. I have constant temperature, I have standard temperature and pressure for all of these, and I have all of them to have same volume of 22.4 liters. Obviously, I will have 1 mole of H2, 1 mole of O2, and obviously 1 mole of N2. Should have been there. Any problem here, guys? Do you have any problem here? Do you understand how is it 1 mole? I'm telling that I have same STP, same standard temperature and pressure for all of these vessels, right? And I'm telling that they're occupying a volume of 22.4 liters. So what do you mean by that? Go by the definition, or you can go by the formula. What is the given volume? Given volume here is 22.4 divided by 22.4. What is the number?
Will be 1, sir.
1.
Yes.
Or you go by the definition, 1 mole of any gas will occupy a volume of 22.4 liters. Here they're occupying 22.4 liters. So how many moles? 1 mole. Either way, it is going to be 1 mole, right? And obviously, if I have same number of moles, can I say that they will have same number of particles also?
Yes, sir.
Is it not? Right? So that is what my statement says. At constant pressure and temperature, same volume, the volume should be same for all these. Then same volume of different gases will have same number of particles. That's what the statement says, right? And obviously, if you're going to increase the volume, the number of moles are also going to get it is the other way around. Like if I include more and more amount of gas, if I increase the number of moles of the gas, then obviously the volume will increase, right? So volume and number of moles are directly related, but we will not see the mathematical form of it because it is not important. Not important, right? It is not. It's not logical enough to look at it like in mathematical ways. Okay, so what I understand is if there is more amount of gas, more particles of gas present, obviously the volume of the gas also gets increased. That is logical. Okay, so everybody understood the statement, right?
Yes, sir.
Same volume of gases will have same number of particles or eventually same number of moles. Okay, so these four are the laws, right? And tomorrow's class, what will we do is we'll be connecting all four of them, all these four laws, and I'll give you a very simple, beautiful equation. Okay, and before that, next class we'll be doing problems on all of these, right? We'll do some good number of problems. Sir, I have poor connection, so I'm not able to hear you when you called. Okay, no problem. Oh, no problem, Manisha. Right? Okay, so what I was telling is, yeah, tomorrow's class, first we'll do good amount of problems on all these laws, right? And then I'm going to give you a crisp, beautiful equation. That is going to be called as an ideal gas equation, right? So have they taught this chapter? Have they given you ideal gas equation in your school?
No, sir. They are doing hydrogen, sir. Currently, they finished redox and
They
they're doing
started.
hydrogen.
Hydrogen, they didn't take it out in the CBSE thing, like when they reduced the portions.
I don't think so, sir. They reduced some parts of it.
Okay, and guys, I'm really sorry. Hydrogen chapter, I will not be teaching you. There is nothing to study there. It's just pure theory. And if I teach you, it will be very boring. So use your school and you can go through your book. And if you have any doubts, definitely you can ask me. Right? So hydrogen chapter and even your environmental chemistry, all these chapters and all, I'll not teach. Okay, I think environmental chemistry is taken out, but still, even if it was there, I wouldn't have taught you that chapter. Okay. Fine. So why will I not teach? It's not like I should not teach. If I teach, there is no point in teaching. Anyways, I'll be telling the same points that are there in the book. There is nothing to logically explain as such. Okay. Fine. So I think that's it for today, people. Okay. So tomorrow's class, day after tomorrow's class, we'll be solving some good number of problems, and I'll give you the equation, and then we'll see that after some 2-3 classes, we'll see that none of the things which the study is correct. Okay. We'll disprove again all of them, because what we see here, maybe not exactly completely proving it wrong, but not in a way in which these are explained here. Okay, so why? Because these gases, whatever I'm talking about, whatever the gas molecules I've been talking about, I have been assuming that all these gases are ideal gases. Ideal means perfect gases, right? But in real life, I really don't have anything to be ideal. That means perfect. I always have some problems, right? So there is a concept of real gases coming after 2-3 classes, right? So when I study about real gas, that is real life situations, right? Eventually you'll see Boyle's law, Charles' law, your ideal gas equation, all these things will actually be not true. Not exactly true in all the points, all the conditions, it is not going to be true, right? So we'll kind of disprove again when I go for real gases. And after that, we'll be studying little about liquid state, how to convert gaseous state into liquid state, right? And yeah, and that would be the end of the chapter. Okay, right? So any questions from today's class?
No, sir.
Any questions from previous chapters? Like, did you went through some problem and you weren't able to solve something like that?
Sir, I forgot to remind you, sir. You told to remind you.
Oh, what was that? What
About
was the
Daniel cell. About Daniel cell.
Oh yeah, now I think I'll do it. Okay, it will take just 5-10 minutes. Guys, can you wait? It's only 3 more minutes for 8 o'clock. Max will finish at max 8:05. Is it okay? Can we start?
Yes, sir.
Okay,
Yeah.
5 more minutes or max 8 more minutes. We'll complete it. Okay. Okay, people, right. So the thing is, you will be again studying this in 12th class, but still, like, since they have given it in your book, we will see that. So when I say cells in chemistry, right, when I say cells or batteries in chemistry, right, I have two types of cells, right? I have one is what is called as your galvanic cells, and the other one are what are called as electrolytic cells. We will not go into the details, right? So your Daniel cell basically, which is there, is an example for galvanic cell, right? If we have time some more, like maybe tomorrow we'll speak about this, what do you mean by electrolytic and all that, but still we'll just complete it very quickly. So your Daniel cell, which is there in your syllabus, it comes under galvanic cells. Okay, so in nutshell, how can I put the difference between your galvanic and electrolytic cells is that galvanic cells produces electricity, right? Galvanic cells produces electricity, right? And your electrolytic cell uses electricity. Basically, here I'm basically here in both these cases, some redox reactions are involved, no doubt about it, right? There are going to be some redox reactions involved, right? But here, what I'm going to do is in galvanic cells, obviously I know I'm going to have certain reactions where energy is getting released, exothermic reactions, I would say, right? So that energy is taken, right, and that energy is converted into electrical energy, and that's what is happening. That's why when I say it produces electricity, how is it able to produce electricity is because I'm going to take some exothermic reactions, redox reactions, and that heat energy or that chemical energy is converted into electricity, and that's what happens in your galvanic cells, right? And in your electrolytic cells, I am going to use electricity in the sense certain things for certain chemical reactions, they will not happen on their own, right? So I have to supply some energy for that reaction to happen, right? Now, generally, we supply energy in terms of heat or light or something like that. We can even supply energy in terms of electrical energy. Okay. So anyways, so Daniel cell comes under galvanic cells, and we'll see how this looks and how this works. Okay. So in your galvanic cell, I have two vessels, right? Say in this, I have my zinc sulfate, and in this, I have my copper sulfate solution. Okay, obviously from this I can understand that I have zinc 2 plus ions and SO4 2 minus ions. From this I can understand that I will have copper 2 plus ions and sulfate ions. Okay, now I'm going to have an electrode. Like, see guys, this all these terms which I'm telling, electrode, these are what are called as electrolytes. We'll be seeing in depth when I go for 12th class. For now, just understand this. It's very easy to understand also. There's not, even if you don't know the technical terms, you'll be able to understand what is happening. Okay. So now in this galvanic cell, I told you that there is going to be electricity produced, right? So let me check whether electricity is produced or not. So what I do is I connect them with the help of a bulb. Obviously, if the current flows through this, obviously the bulb will glow. Correct? Right? And for completion of circuit, I will be putting something called as a salt bridge also. Again, guys, getting into details will take so much time. You don't have to know what the salt bridge. Salt bridge, just assume that it is going to help me complete the circuit. Okay? And salt bridge, in technical terms, they say that they're going to maintain electrical neutrality. But again, we will not go into the details. We'll just see how this works. Okay, fine. Right. So I have zinc. Okay, and what are these rods? This is my zinc rod, and this is my copper rod. This rod is made of copper. This rod is made of zinc. Okay, very simple. Very simple arrangement. Copper sulfate, zinc rod, copper rod, with the help of a bulb, and obviously one more thing which is there is a salt bridge. Okay, right. Now we have to understand this. I have zinc, I have copper. Which do you think is more reactive, zinc or copper?
Zinc.
Zinc, right? So zinc is more electropositive. That means zinc is having more tendency to form positive charges, correct, than your copper, right? So what will happen is in this side, that is, there are two half cells. See, this is the whole cell, and this is one half cell. This is another half cell. Just how we call half reaction, right? So in this case, I will have one reaction. In this case, I will have another reaction. Okay, so I know zinc is more electropositive, so zinc will form the positive ion. So zinc will form Zn2 plus by removing 2 electrons. Okay, fine. And obviously, if one thing undergoes, this is oxidation, is it not 0 to +2? You see that increase in oxidation number, or in terms of electrons lost, you can say that this is oxidation, right? Okay, now when I go to this side, right, now obviously it cannot undergo oxidation because already zinc has undergone oxidation. So what will happen is reduction is going to happen. I already have Cu2 plus ions here in the solution, right? Now this Cu2 plus ions will accept these 2 electrons to form copper. Now this what happened? I have +2 becoming 0, so obviously it is reduction. Okay, now what do you see? Electrons are getting transferred from the zinc side to the copper side. Isn't it? Electrons are getting transferred. You can see that the zinc has lost 2 electrons, right? And these 2 electrons are accepted by copper 2 plus, right? So what is happening? So obviously the electron flow is from this direction to this direction, right? And I know what will be the direction of current. Obviously, you will know this. Whichever is the direction of electron, the opposite direction is the direction of current, right? So if this is the direction of electron, this is the direction of current I. So obviously, there will be some electricity produced, and your bulb glows because of the movement of electrons. The current is flowing from this side to this side. The bulb glows. Okay. This is the working of galvanic cells. Any doubts from this? Actually, I didn't tell you most, like some things, like there are so many other very minute details which you can concentrate on here, but still for your level it's not important, and we don't have time also for that. When we go, we will spend very good quality time when we go for 12th class studying this chapter, electrochemistry it's called. Okay, so any doubts, people? Everybody understood what is the working of this galvanic cell, or say Daniel cell?
Yes,
Understood,
sir.
sir.
Okay, fine. If you still have doubts, you can ask me tomorrow. Sir, this is how and what is that? We can discuss, no problem. Okay, fine, guys. Thank you so much. Exactly 8:05. See? Okay, bye bye. Thank you.
Thank you, sir.
Thank you, sir.
Thank you. Thank you.